Hello everyone, my name is Passang Doma Lepcha, having roll number 21NS0174 of BSc third semester, and my topic for sessional B is MBE technique. Firstly, I would like to show my gratitude to my teacher Dr. C.P. Khatiwada sir for giving me such an interesting topic for preparing my PPT. Now, let's discuss content of the topic, that is introduction, diagram, principle, theory, application, and reference. Now, firstly we will discuss intro part. Molecular beam epitaxy is a process in which a thin single crystal layer is deposited on a single crystal substrate using atomic or molecular beam generated in stem cell contained in an ultra-high vacuum chamber. Molecular beam epitaxy, invented by Alfred Chow and John Arthur at Bell Labs in 1968 and developed in the 1970s, enabled the controlled deposition of single atomic layers. Molecular beam epitaxy is an evaporation process performed in an ultra-high vacuum for the deposition of compound of extreme regularity of layer thickness and composition from well-controlled deposition rate. And this is the diagram of molecular beam epitaxy, MBE. In this diagram, we can see red gun fluorescent screen, stationary substrate heater, beam flux monitoring gate valve, viewport, rotating substrate holder, quadruport, mass spectrometer, sorter, effusion cells, liquid nitrogen cooler, pan. Now, moving to the principle, molecular beam epitaxy is a technique developed in the 1960s in the Bell Laboratories and is widely used in semiconductor research to grow very high quality single crystal multilayer of 3-5 semiconductors, or MBE system is dedicated to the growth of metal and more recently oxide thin films and heterostructures. The basic principle of MBE growth is the direct sublimation of solid source materials into a gas phase at very low pressure. Typically we use 10 to 10 mbar because the gas pressure is so low. The individual molecules and atoms are able to travel many centimeters before they collide with another molecule. This means that everything inside the MBE chamber gets coated with a very even and very thin layer of material being deposited. Because the deposition rate is very low, the atoms that land on the substrate have plenty of time to move around and settle into a single crystal structure before they get burned under the next layer. Our MBE system can grow 6 different materials in one deposition cycle. 3 relatively low melting point metals can be grown from the quantum effusion cells, and for higher melting point materials there are 3 electron beam hulls. During growth, the flame structure can be monitored by in situ reared. A feature of our MBE system is that the substrate manipulator, which can heat substrates to over 1200 degrees Celsius, is equipped with a series of marks that can slide in front of their substrate to pattern the growing flames. Theory: Molecular beam epitaxy is an ultra-high vacuum thin film deposition technique. MBE is widely considered the most controllable and highest purity form of deposition and is currently used in both R&D and high volume production. Most MBE growth result in high quality epitaxial thin flames, solid source of high purity growth material are placed in crucibles typically made of pyrolytic boron nitride. These crucibles are heated to the required evaporation temperature for the given material, resulting in directed vapor flow of evaporation material towards the substrate to be deposited on. Mechanical or pneumatically based slutters are placed just above the crucibles, allowing the abrupt and accurate start or stop control of the deposition process. Because of the purity of the source materials are the ultra-high vacuum environment, typically based pressure in MBE are 1 into 10 to 10 m bar or less. The deposition material is of the highest purity. Combined with accurate control of the substrate temperature through atomic layer by layer deposition can be achieved, along with atomically abrupt interface between layers. Using the right tools to measure and control this process is crucial for quality and efficiency. While there are a number of vacuum companies that make custom MBE systems, there are only a handful of commercial MBE reactor manufacturers worldwide. Key Space works with Vico, River, DCA, SVT, Omicron, Eco, and Enilva to ensure proper fitment and even adventured communication into the growth control software. Keyspace tool can be found worldwide on all these MO reactors. Characteristics of MBE. Number 1. Fast switching for superior interface. Number 2. Able to grow thermodynamically for forbidden material. Number 3. No hydrogen passivation, no burn inherent to MOVPE. Number 4. Uniformity, easier to tune, largely set by reactor geometry. Now application. Molecular beam epitaxy technology is now widely used for growth of single crystal thin flames, quantum wells, superlattics, and similar structures. The MBE system was developed first as a research system for preparation of single crystal thin flame and superlattics. Soon, many people wanted MBE system for production of electronic and optical devices and some kind of sensors. By using the production MBE system, mass production of compound semiconductor thin films could be performed under the completely closed process without the influence on environment. However, it was not too easy to work to realize such production MBE system. MBE is thought to be one of the most promising and powerful thin film growth technology used for growing single crystal thin films, quantum well or superlatics, and so on, many mainly from 3 to 5 compound semiconductors. Thin films of narrow gap materials such as InSB, InAS, and related compound semiconductors were easily grown by MBE and showed high electron mobility. Therefore, the MBE system have been used for production of electronic device and magnetic sensor for more than two. Production technologies of narrow gap 3 to 5 semiconductors, thin films made from INSB, INAS and related materials growth by MBE, and sensor applications are discussed. The application to high sensitivity magnetic sensors such as INSB thin film Hall element and INSB thin film magnetoresistor are demonstrated. Moreover, in the last section of this topic, the application to infrared sensor of narrow bandgap materials growth by MBE is discussed. Although the mid-infrared sensor operating at room temperature without a cooling system have been required for a long time, it was very difficult to realize. However, we have succeeded in developing uncooled INSB photovoltaic infrared sensor operating at room temperature. In this topic, the MBE growth and device fabrication of PIN based INSB photovoltaic infrared sensor are described. Then the device performed of INSB photovoltaic infrared sensor at room temperature and their application to temperature measurement are demonstrated. And lastly, I reference from this website, that is Handbook of Deposition Technologies for Films and Coating, 3rd edition 2010.